Welcome back. In this video, we are now prepared to study systems with complex eigenvalues. So recall that we looked originally at homogeneous, constant, coefficient, first-order linear differential equations and second-order differential equations. One of the things that we'll notice here is that when we are finding these eigenvalues, they actually correspond to the roots that we would find in our guesses e to the r1, e to the rt for second order differential equations. The cases that we've considered are where we would have two real roots, where we would have one repeated root, and where we would have two complex roots. So the first case we have already tackled with respect to systems. The next two cases are really similar to that of second order differential equations. We won't focus on the one repeated root, but we will look now at two complex roots. So imagine we have a system. This is a first order, homogeneous, because there's no plus g of t tacked onto the end of these guys. First order homogeneous, constant coefficient, linear systems of differential equations. And we have to be this specific because if any one of these features changes, for example, the constant coefficients, then our methodology doesn't really work anymore. So A, B, C, and D could, in theory, be functions of time. So A, B, C, D are all real numbers. Further, suppose that the system results in complex eigenvalues in which it is the case that lambda equals g plus or minus hi, where g is the real part and h times I is the imaginary part of the eigenvalues. Then the general solution is this big gigantic mess. We won't derive this, although I do have a derivation I can share if you are interested. But let's look for a second at what this means by g plus or minus hi. So for example, if I wrote 3 plus or minus 2i, 3 is the real part. So g is 3. And this is the real part. And actually, I really should say h equals 2 is the imaginary part. Okay, and so what we mean by I is a lot of times when we take the square root of a negative number, for example, times where some point in your experience when you use the quadratic formula and you had something like negative 3 plus or minus the square root of negative 64 over 2. And what we would do with that negative 64 is we would break it up into two factors, one being negative 1 and the other one being 64. So now what happens with that is if you take the square root of a product, that's identical to taking the square root of each of the factors in that product. So the square root of negative 1 times the square root of 64 over 2. And the square root of negative 1 is what in mathematics we call I. It stands for, it's an imaginary number. It still occurs in real world situations. Square root of 64 is 8, so we could write this as negative 3 plus or minus the square root, negative 3 plus or minus 8i over 2. So let's delve into this. You can see a lot of these components in here are coming from either the system of differential equations or the eigenvalue. Notice that we don't directly use any of the eigenvectors in here. They're already taken care of. So you do not have to worry about grabbing the eigenvectors. We only need the eigenvalues. So notice that A, B, C, and D, A is a component that gets inserted in certain spots. B is a component that gets inserted in certain spots. And you can see those guys there. C and D, however, do not appear to get inserted into this equation, and that you might say, well, they don't matter, but in fact they do matter because A, B, C, D is the matrix that we use to compute the eigenvalues in the first place. They just don't directly fall into the result. The other thing to notice is that the real part, G, ends up being an exponential coefficient. So it could be positive, it could be negative, and you could see that if this would be e to the positive something t, then this would result in exponential growth, And if g was negative, then we'd have some sort of aspect of exponential decay. The h, and g also kind of happens to go into one of these coefficients here as well. Now, the imaginary part, h, actually controls the frequency of the sinusoidal components of these functions, and also happens to go in as a coefficient. But most importantly, notice that h, the imaginary part, is going to control how rapidly the sine and cosine functions oscillate. So let's consider a system. Here we have dx dt is 3x minus 13y, dy dt, little dy dt, is 5x plus 1y. And when we compute the eigenvalues of this, we notice that we get lambda 1 is 2 plus 8i, and lambda 2 is 2 minus 8i. Notice that they're identical, except that one has a addition sign, one has a subtraction sign. These are what we call complex conjugates. And they always come in pairs. So when you'll always notice that for a system, you're going to have the real part, g plus or minus hi, will cover both eigenvalues. So to piece this all together, the first thing we should do is identify what the components are. So we know from the matrix that A is 3, B is negative 13, C is 5, and D is 1. We know from the complex eigenvalues, here we have G, here we have H. Notice that H is always going to be, we're always just going to take the absolute value of the H. So up here in our definition, we say G plus or minus HI. So H itself is going to be a positive quantity, but it's going to be added in one of the eigenvalues and subtracted in the other. So we are just going to, for G, we do take its sign. In this case, it happens to be positive 2. H, we ignore the sign, it's going to be 8. So now really what this boils down to is plug and chug. And so the y vector, recall what that has in it. That's just our two dependent variables. So x and y equal. And now we can start plugging things in here. So we'll have k1, that's our arbitrary constant, e to the 2t, times, inside the parentheses for the x component, we'll have cosine of 8t. So h is 8. And for the bottom component, we'll have negative a plus g over b. And that might be something I want to do off to the side, so I don't have to keep writing in that big fraction. So let's go ahead and just write that down, figure out what that coefficient is, and then worry about plugging it in. So that's going to be, let's see, negative a plus g over b. That's going to be negative 3 plus 2 is negative 1. Negative 1 over negative 13 is 1/13. Okay, so this coefficient here will be 1/13 of cosine 8t. Also, the other thing I'm going to need is h over b, which is 8 over negative 13. Oh, I'm sorry, now that's not h, that's h over b. So h over b is going to be 8 over negative 13. So here we're subtracting it, minus h over b, so this will be plus 8/13 sine of 8t. And that completes that term, plus k2 e to the 2t, g is 2. And a lot of this stuff is going to look very similar, except the top component is going to have sine of 8t, and the bottom component is going to have the same coefficient as the cosine did here, 1/13 sine of 8t plus h over b. We said h over b was negative 8/13, so we're adding it, so plus negative 8/13 cosine 8t. All right, and we could split this up into the x function and the y function. So let's go ahead and do that just to demonstrate. Now the y component looks really tricky, but a lot of these terms that are as a result of the eigenvectors, and the eigenvector I intentionally chose to make the top component a little bit simpler, only because we'll see in a moment that for spring mass systems we can decompose the system into a system of two differential equations, one of which will represent position and the other one which will represent velocity. So if I now distribute this through k1 e to the 2t times cosine 8t, and this should look familiar from working with Laplace transforms. We came up with these types of solutions with Laplace transforms as well as with second order equations. And here we'll have plus k2 e to the 2t sine 8t, and that's the entire solution. So for a spring mass system, that's a very likely solution where you have damping and end up with complex roots. And the bottom component is going to be a little longer. It's going to be y equals, now k1 e to the 2t gets distributed to both terms here in the parentheses, so k1 e to the 2t, well, the 1/13th I'll factor out, 1/13th, and this is cosine 8t, that's the first term. Now distribute to the second term, that's going to be plus 8/13 k1 e to the 2t sine of 8t. I'll do the same thing for the second guy here, k2 e to the 2t distributed to the 1/13th sine 8t. So 1/13th k2 e to the 2t sine 8t, and then distribute it to the minus 8/13th cosine 8 to the t, or minus 8/13th cosine 8t, which would be minus 8/13 k2 e to the 2t cosine 8t. And that's the full-blown solution. Now, to find initial conditions for k1 and k2, this can get a little cumbersome because we would need initial conditions for both x and y. And so once we substitute in our t equals 0, we're going to get a pretty, I shouldn't say ugly looking system, because of the sign of 8 times 0, those will go away. So we'll get a system of equations here if we get an initial condition. And a lot of these terms will reduce when you plug in t equals 0. So you'll be able to solve for k1 and k2 pretty quickly. Now, this would not have been so easy with working with second order equations where you actually had to take the derivative of this big mess. So anyway, that is the solutions. The reason I wanted to write this out in particular is because the first thing we should notice is in this solution, and if we just kind of thought about the 2 as the g and the 8 as the h, what we're noticing is that g controls the amplitude. So if we have something like this, if we have g is greater than 0 for this system, then for both x and y, what we would observe is that, well, if g is bigger than 0 and all I have is an exponential times a cosine and an exponential times a sine, they're all have the same frequency. So what I would see is if g was bigger than 0 like it is here, is the oscillations would progressively get exponentially larger. And we would see kind of something like this, versus if g was less than 0, that would mean we'd have like e to the negative 2t, and that would be an exponentially decaying sinusoid, and that would look more like this, something we've seen before. And again, exponentially decaying amplitudes, we would see that we could contain that. Now, one other case, what if g is 0? Well, if g is equal to 0, that means the exponential piece is e to the 0, and you're just left with 1 times cosine 8t, 1 times sine 8t, with a k1 and k2 in there, of course. Those will just control initial conditions. But with g equals 0, the exponential piece is just 1, and so there is no exponentially changing sinusoid. It just oscillates. It's basically the equivalent to saying no damping at all in a spring mass system. So as a result, that helps us think about what's happening to both x and y, because x and y are both doing this. They're both doing the same thing. It just so happens that y has more terms in it, but they are all same e to the gt cosine ht or e to the gt sine ht with just different constant coefficients. So that being said, we're now ready to classify the remainder of our phase planes. So we've already described the first three here. We already created a division here saying if we have lambdas that are real, we're going to be contained to or confined to these top three scenarios. So as I like to call this, instead of an unstable node, I like to call this a source, because all of the solutions are sourcing away from the equilibrium. This was when both eigenvalues were positive. So real numbers. Here we had all of the solutions going in towards the origin, so this we call a sink, and this is where both lambdas, lambda 1 and lambda 2, are less than 0. Then the third case, where 1 is positive, 1 is negative, we get what looks like a saddle, so a saddle point. So this, we do stick with the word saddle, and this is where one of the lambdas, doesn't matter which one, I'm just arbitrarily writing it as lambda 1 bigger than 0, lambda 2 less than 0. Now, the last three cases are complex. So these are all complex. If we had a g value of 0, and it all depends on the g value. The h value isn't going to control the behavior, it's going to control the speed with which that curve oscillates. So if this were cosine 10t, it would still, all three of these scenarios would persist, but with 10t we just have more compressed oscillations because the frequency would be 25% higher in that case. Now if g is 0, both x and y are just oscillating. They are never getting closer to the origin, they are just oscillating around the origin, the point 0, 0, and so we get what's called a center. And this is where, when you have, so complex eigenvalues, we said lambda equals g plus or minus hi. So this is when, right here, g is equal to 0. Now think about what that means. This just means no exponential amplitude. Took me a second there. Now, here we have solutions. You can see the arrows point away from the origin. By the way, none of these have straight line solutions because they don't have real eigenvectors. In the first three cases, the reason we had these straight line solutions was because we had real eigenvectors. Here in the real plane, you cannot visualize imaginary eigenvectors, and so we end up getting this behavior like spirals. So this is called, I like to call this a spiral source instead of an unstable spiral, because all of the solutions spiral away from the origin, and it matches our nomenclature from above for just the regular source. And this is going to happen whenever that g value is bigger than 0, because notice that the oscillations get bigger and bigger and bigger. And this is called, I like to call this a spiral sink. Again, similar idea here. All the solutions are moving inward. They're getting closer. They're oscillating around the origin, but they're sinking into it. And this is when g is less than 0. So you can now sketch the phase plane just by knowing the eigenvalues. And when you get a complex eigenvalue, you can completely ignore the eigenvector when you're trying to sketch the phase plane. Pretty cool. So where do we realistically see complex eigenvalues? Well, the most obvious case will be the damped spring mass system, where the oscillations stop or progressively stop because of resistance, some sort of friction, wind, air resistance, gravity, etc. What's often desirable is to decompose this system. This is called a decomposition because we are going to break this up into two first-order differential equations, in fact, a system. In order to do this, there's a little, not actually even call it a trick, but it kind of is a trick the first time you see it. We're going to create a new dependent variable called v, and we're going to assign it dy dt. So basically all we did was we just assigned the velocity of the spring mass system to a variable called v. Let v equal dy dt be a new differential equation that simply represents velocity. Now, if we let this substitution take place, if we take the derivative of both sides of this equation, the derivative of velocity is the derivative of velocity, right? So the derivative of velocity, dv dt, is the derivative of dy dt, which is the second derivative of y with respect to t. So basically that just means that change in velocity is acceleration. And now what we can do is we can substitute into our original equation. So what we're going to do is we're going to replace the second derivative with dv dt. That's based on this. And the reason we did that is because now we have the blue v equals dy dt and this equation are both now first order. They are a system because they do depend on each other. You can see that this guy now depends on v, and this guy depends on v as well. This guy depends on both v and y. The other thing that we're going to do is then we're going to substitute dy dt. We're going to replace that with v because that's the substitution we initially made. And if what I do is I isolate dv dt by moving it to the other side, then if I subtract away everything but dv dt, my first derivative, then I'll have minus k over my minus b over mv. And now I have two equations. I have dv dt, which is the change in my velocity, which is basically an acceleration equation. So acceleration equals, and then I have a velocity equation, dy dt equals v. So to put that into more of a matrix looking form, dy dt is really 0y plus 1v, and dv dt is negative spring constant divided by mass times y minus damping coefficient over m times v. And this decomposition is always the same. This never changes, so you don't really have to rederive this, but it is possible to take a second order equation and break it up into two first order equations. So that means that in general, for a spring mass system, this is going to be the matrix. Again, remember that the thing to point out here is that this is the velocity equation. If we solve it, it solves for y. This is the acceleration equation. And if we solve it, it solves for v. All I mean by that is that's the variable that we would get y equals and v equals if we solve these two equations. So this is the coefficient matrix. Let's take a look at an example so we can see how this particular one behaves. We have a mass of 1 kilogram, a spring constant of 6 newtons per meter, and a damping coefficient of 4 newtons per meter per meter. So that being said, an initial position of 1, a stretch of 1 from equilibrium, and a velocity of 0. So here I just copied and pasted the equation so that we would have it, computed the eigenvalues for this matrix. So this matrix is really just 0, 1, negative k over m, so negative 6 over 1 is just negative 6, negative b, which is 4 over 1 is negative 4. When we compute the eigenvalues and eigenvectors of that, we get negative 2 plus I times the square root of 2, negative 2 minus I times the square root of 2, and then the corresponding eigenvectors, which we said we don't really need because that's already built into the solution. So I'm going to just take a moment to identify everything. A, B, C, and D come from my original coefficient matrix. So A is 0, B is 1, C is negative 6, D is negative 4. And then for my G plus or minus HI, I see that G is negative 2, and H is the coefficient of I, which is square root of 2. And then, of course, what we want to compute is just so that we can just plug everything all in one fell swoop. Negative A plus G over B. So that's going to be 0 plus negative 2 is negative 2 over 1 is negative 2. And then finally we can do negative H over B, which is going to be negative square root 2 over 1. So just square root 2. So H over B is just going to equal square root of 2. Okay, well that's all we need in order to build the solution, so let's go ahead and build this. Now let's remember that what's inside of this y vector at this moment is the position and the velocity. So the reason that is the case is because our equations are dy dt and dv dt, so what we'll solve for is the position and velocity. Now it turns out that this second equation, velocity, is not going to be very useful in terms of graphing it. It's just going to really be the derivative of the y equation. So but we do need to use it so that we don't have to go back, and the beautiful part is with second order equations, we had to take the derivative of the position to get the velocity so that we could plug in our initial conditions. But here, it's already part of the vector. So it's really, really nice. It's a faster way to solve that kind of problem. Okay, so we're going to have yv equals k1 e to the gt, so g is -2, so we can see we're going to have an exponentially decaying amplitude. Makes sense. We have a damping coefficient of 4, multiplied by cosine of the square root 2t, and then we will have down here negative a plus g over b is -2 cosine of square root of 2t minus h over b, which we said was square root 2, so minus square root 2 times the sine of square root of 2t. And you can kind of see that the derivative of cosine of square root 2t is negative square root 2 sine square root 2t. The reason we get the extra term here is because it's actually a product rule thing that we would have to do, because we have e to the gt times cosine. So we would have to take this is basically going to end up being what we would get if we took the derivative. So the second term is going to be plus k2 e to the -2t times sine of square root of 2t. And then down here, same thing as the cosine function from the other half, -2 sine of square root of 2t, and then plus h over b. H over b was square root 2, so it's going to be plus square root 2 sine, cosine. Let me back that up a little bit here. Plus cosine of the square root of 2 times t. There we go. And that closes that vector. So now we can write the y and v equation. So y is going to equal k1 e to the -2t cosine square root 2t plus k2 e to the -2t sine square root 2t. So let me take a moment and write that out. So k1 e to the -2t cosine of square root of 2t plus k2 e to the -2t sine of the square root of 2t. And then the second equation is going to be the uglier one. V equals k1 e to the -2t, -2 times that. And you can think about that -2 as being what happens when you take the derivative of e to the -2t. It's the chain rule. And this is cosine of the square root of 2t minus square root 2 k1 e to the -2t sine square root 2 of t. And same thing for the second term, but with the corresponding expressions. So this should be a -2 here, so let's go ahead and fix that. All right, so here we go. -2 k2 e to the -2t sine of the square root of 2t plus k2 e to the -2t times cosine of the square root of 2t. Oh, we forgot a square root of 2 here. So let's go ahead and try that again. Okay, and there we have it. So next, all we need to do is just go ahead and plug in our initial conditions. So we already have the initial position as 1 at time 0. The initial velocity at time 0 is 0. So if I do some substitutions in here, the position is 1, k1 e to the negative 2t, when t is 0, all the exponential pieces will be 1. So we'll just have 1 equals k1. Cosine of square root 2 of 0 is just going to be 1. Cosine of 0 is 1. So this will just equal k1. And then here, when we plug in 0 for sine, that's going to be 0. So this whole second term is going to go away. Well, nice. We've just solved for k1. The initial condition for v is 0. So if we plug in 0 for the sines, those are all going to be 0. So these two terms here will cancel out. And we'll only have the first and the last term, which will be negative 2k1. Again, e to the negative 2 times 0 is 1. Cosine of 0 is 1. And then the last term here will be plus the square root of 2k2. So now we can solve for k2. We already know what k1 is. k1 is 1. And so here we can do a quick substitution, probably faster than going to Wolfram alpha. And now we can solve this for k2, which is relatively quick. All we need to do is just add 2 to both sides and divide by the square root of 2. So we get k2 equals 2 over root 2. Now, we don't need the velocity equation, so it's not like we need to deal with v again. This, remember, is just the derivative of y. So you can take the derivative of y and see that you get v as expected. All we really need is the position equation. So this guy here, we're just going to plug in k1 and k2, and we've got our solution. So y equals k1 e to the negative 2t cosine of square root of 2t plus 2 over square root 2 e to the negative 2t sine square root of 2t. And there we go. We have solved our spring mass system. And that's it for this video. We're done with complex eigenvalues. Next, we'll start to look at how does this apply to nonlinear equations.